Hi all, welcome again. In this section of the video, we'll be going through a couple of experiments with respect to the real world use case scenario. I have already discussed with the experiments related to the Sydney Harbour Bridge using a simple auto encoder and the robust auto encoder in section 2 and 3 respectively. So in this section of real world use cases, I'll be focusing on the experiments related to the deep SVDD and the soft version of the deep SVDD and the one class neural network approach. So let's get started. Yeah. So as you can see in this notebook, like with the ID 05 real world use cases, once you have loaded the once you have executed the prerequisites such as mounting the directory and ensuring that you have the right path, so you can come down to the section of the deep SVDD based experiments, and then this experiments will be using the preloaded FFT features which have been computed and stored in the mat file. So yeah, so in here in this section we are defining the class which contains the implementation of the one class deep SVDD implementation, and in fact the same class contains the implementation of all three variants of the experiments, as these two experiments, such as the soft version and the one class SVDD version, can be seen as a hypersphere implementation, whereas the one class neural network can be seen as a hyperplane implementation obtaining a hyperplane to separate the normal data with the anomalous data. So I'll take you through the implementation of these algorithms and see how things are how the inputs, what kind of inputs are being considered, and how the anomalies are being detected. So in here we are defining the configurations related to the experiments, and this is a very important file where you could set up different configurations, and you're also setting up the different hyperparameters related to the architecture of the auto encoders being used and what kind of architecture you want to use. And in fact it could be extended to different sets of data sets, and data set specific configurations are also being mentioned here. And also the path of the data file which needs to be loaded, which contains from which the training and the test set will also be created, is also being mentioned here. So this is a very important file to familiarize yourself. So let's go back to the cell, and we defined a set of paths for storing the results and the related weights, if you want to store the weights of the trained model as such. And we could here I defined a random seed just to make sure that we run the experiments iteratively over 10 times with 10 different random seeds, so that each time you run there is a different set of train and the test samples which are being created. So this ensures we are testing the reliability of the algorithm across different variants of the train and the test sets. So as for the sake of simplicity, I've just considered one random seed, so that means this just runs for one loop, and being computing the balanced accurate the AUC in this case, computing the AUC score for all the three algorithms in this case. So the design of the execution is following a very similar to the sklearn approach, where we have the fit and the predict function. These are the two important functions which determine the life cycle of the algorithm. And in here we are initializing with the relevant initialization variables which are required for the algorithm. So OCNN broadly refers to one class neural network based family algorithms. So this is an object being created here by calling this class. So this instantiates the data loading capability of the algorithm, and once the data is loaded, we try to fit with the trained using the train data and then predict using the testing data. We'll go into the code and see the detailed implementation of each of the section. And for each random seed, I compute the AUC score, and finally we obtain the mean and the standard deviation of the AUC, which are computed over the 10 different random rounds. So let's get into the class, one class SVDD, and this could be found within the directory like SRC models and one class SVDD path, which I have opened for you. So if you want to locate it, you could do it like this, like one class SRC models and one class SVDD. So here I have opened it for you in here. And let's take a look at the one class SVDD initialization class and see what's happening here. So let's go to the top of the file. Yeah. So there is another class defined, adjust SVDD radius. I'll come back to this a bit later on. So this is the class with what we are referring to, and it performs the initialization of the parameters which are sent, and depending on the type of data set, we might have to customize and massage the data and normalize the data accordingly. So we're just focusing on the SHB, and we focus on the SHB data loader file, which is the code has been written in a very modularized fashion so as to accommodate n number of data sets in future. So here we just focus on the data, and we focus on the shb.py, which I have opened it for you here. And depending on the configuration settings, the respective data will be loaded, and the transformation functions will be applied accordingly. In our case, we are loading the SHM, the Sydney Harbour Bridge, the two joint data sets with already known anomaly being present there. So since we already computed the FFT, so we would be using the flag as 0 in our case. So this is the function which loads the data, and a min-max normalization is also being performed for the normal as well as the anomalies, and depending on the number of training samples which you want, which is defined in the configurations, which is configurable, the test and the train data is numpy arrays are created and written for the algorithm to use. So this basically sets up the data, the train and the test data for the algorithm. And moving on, once the train and the test data is set up, we move on to the we try to fit using try to fit the train data which is obtained. So let us go to this function here, class here, and focus on the fit method. Yeah. So this is where the control is reached once you call the fit function. So in here we have let us go through at the high level what actually is happening. We are having a switch between three kinds of loss functions. If it is a soft bond deep SVDD or a one class deep SVDD, it's a minor difference between these two, wherein we subtract the radius which is computed in one case, and we do not subtract the radius which is computed in the other case. So going on, if that's a slight more difference between these two type of architectures, and both can be experimentally seen and tried for yourself. So once we hit this type of loss function, we obtain the training data which we have prepared in the previous step, and then we pre-train the convolution. We pre-train the autoencoder, or it could be a convolution autoencoder if you are considering the set of images. Image scenario. And please recall the architecture of the deep SVDD and the SVDD was discussed in detail in section 2. It involves pre-training the autoencoder first, and obtaining the weights of the autoencoder, and then attaching a dense layer at the end of the encoder network to obtain the representations. in order to obtain the representations and formulate either a hypersphere or a hyperplane based loss function. So in here, kindly refer to the slides related to the deep SVDD, which is discussed in the section 2 of the tutorial, and yeah, for the theoretical formulations have been discussed in the section 2. Kindly refer to that section to get more understanding about the theoretical formulation. So in here we are focusing on the code aspect of it, and yeah, so moving on, we have the deep SVDD one data set, and we train the autoencoder first, and using this using the pre-train function, we get the train data set, and we initialize the center and the radius of the SVDD implementation in here, and here we add, if it is depending on the type of data set, we add a dense layer, and this could be completely optional. You could add more than one layer, and that defines your kind of architecture and your data set. Depending on the data set, you might have to change the number of layers which you add at the end of the encoded implementations. And then we define a callback functions, and this class which we have defined at the beginning of the file is the callback function, which is called at the end of every epoch. So in here we have defined on the we have called a callback function, wherein at the end of each epoch we try to adjust the value of radius which is computed according to the algorithm. We're taking the nth percentile or the qth quantile of the value which is value of the representations. So in here the value of r is updated at the end of the radius is updated at the end of every epoch, and in case of one class neural network implementation, the way there is no center term, and the way we compute the distance is slightly different between the deep SVDD and the hyperplane implementation. So in here we are computing the distance between the representation to the center variable, and we obtain the scores. We obtain the scores and subtract the subtract the center from the representations, and we sort the values of the scores which are obtained, and take the qth quantile representation of the same. In case of as a slightly variant of one class representation, you could simply obtain the representation and the distance very similar in both cases. So the way the distance is computed in one class neural networks as well as the deep SVDD is very similar here, except for the way the loss function is defined, which we'll get into in a moment. So once we have this callback function called, so we have the callback function called to update the value of r at the end of each and every epoch in here. So this takes care of the portion of updating the value of r. And since we have already defined the architecture of the deep SVDD, we are adding one dense layer in this case, and we are choosing the custom Ocean and hypersphere loss function. So let us go to the hypersphere loss function in this case. Yeah, so depending on the value of the r that is being updated, and the center which is being updated at the end of each and every epoch, we're defining the custom ball implementation, where the distance is taken to be the difference between the predicted variable and the center, and the mean of the distance is taken in case of spherical hypersphere loss function implementation, whereas in case of hyperplane loss implementation, we derive the loss function by incorporating a hinge loss as against the square difference error. The theoretical formulation of the one OCNN forming using a hinge loss formulation has been discussed in the section 2 of the tutorial. So I kindly suggest you to take a reference of those theoretical formulation to have a good understanding about this implementation. So having defined the loss function and the architecture for both the for either following the deep SVDD or the one class neural network, we are going to train the network using the fit function, and define the validation split, and as well as the hyperparameters, and finally we save the radius as well as the center which is being obtained in case of in case of the deep SVDD and the SVDD approaches. So as I was previously discussing with you, in case of a soft bound, we obtain the final scores. The final scores were obtained where the distance is subtracted, with the radius is subtracted from the distance which is computed, and the threshold is set as 3 standard deviations away from the scores, and which would be very useful for computing the labels and evaluating the metric. And in case of one class deep SVDD, we just take the scores to be as the distance in this case. So if the loss function is one class neural network, the things are performed very similar to this, very similar as compared to the deep SVDD approaches, except that we could define here again we are pre-training the autoencoder and detaching the decoder layers and keeping the weights of the encoder, and adding a dense layer at the end, adding a flattened dense layer at the end to define the architecture. So once we have defined the architecture of the one class neural networks, so we are in a position to train the network and update the radius at the end of each and every epoch, and we also set suitable learning rate and to train the model, and we obtain the parameters with respect to the hypersphere loss function, and in this case also we consider 3 times standard deviations to be as a threshold considerations. So here we looked at the fit function, which basically involves building pre-training the autoencoder and throwing away the decoder portion of the autoencoder and just keeping the encoder section by loading the weights, and wherein the architecture is modified by adding a dense layer at the end of the encoder network. So n number of different number of architectures could be formulated depending on the nature of the data set, and hence we could derive different versions of the network to experiment, which experimentally find which architecture produces the best results for a given data set. So having defined the fit function for the one class SVDD and the soft bound as well as the one class neural network, once we have trained the model, we evaluated using the test data using the predict functions, and in our case, since we are loading the pre-trained FFT values, so we could see that the trained data consists of the dimensionality of 1800 in this experiment, and the test data is having about 21,000 samples, 21,652 samples, out of which the 1,000 samples are taken to be healthy, and the damage samples are about 20,652 samples, and the training data consists of only healthy data of around 4,983 samples of healthy data. And as you could see, firstly we are compiling the autoencoder, we are pre-training the autoencoder, and then we are trying to define, we are trying to initialize the value of C and the value of R, for which, and after that we are defining the hypersphere loss function for the defined architecture of our choice, and then computing the predictions for the test set. And as you could see, the performance of the deep SVDD is yielding about 0.9 AUROC for about 3 different runs here. And you could run these experiments yourself and try to understand and experiment and customize for your specific data sets. So in here I covered the implementation of deep SVDD and the soft version of deep SVDD. It is another cell. You can, as a hands-on exercise, you can try to run and change some of the parameters within the code and see for yourself. And this section of the cell contains the one class OCNN based experiment. You just have to change the flag to choose a different loss function to execute different various set of algorithms. And we have shown you in this session. We have shown you how we used the deep SVDD, the soft bound as one class OCNN models for our real-world Sydney Harbour Bridge datasets, and we have also conducted experiments based on laboratory specimens based data based bridge structures, and the results seem to be quite similar to the way the autoencoders are performing for our datasets. So as such, the deep SVDD or the softbound as well as the OCNN performs relatively closer, or not. They don't offer much significant advantages when compared to the autoencoder or the one class support vector machine in this data sets for our specific data set. But nevertheless, one could work on leveraging this kind of architectures for their defined data sets and see how they outperform, or how this algorithms can be tuned by choosing the relevant hyperparameter, how this could be leveraged for your specific data sets. So I hope you enjoyed the real world use case scenarios for the algorithms. And any questions, I'll be around. Please ping me to discuss more about the implementation part of it. Yeah, see you soon. Thank you.